Our next speaker is Alex Slamen from Toronto. He's going to tell us about studying class groups as Selmer groups in quadratic twist families.
Okay, thank you to the organizers for putting on this lovely conference and for giving me the opportunity to speak. I have a unique lecture. I'm going to be trying to link the two. So far we've heard Julia talking a lot about number field and class field statistics, and Alex has been talking about statistics of Selmer groups and quadratic twists, and the point of this lecture is to sort of show that the stuff that Alex is doing can be used to study some questions from Julia's lectures. I should mention that basically the only references for these talks come out of Alex's papers. So if I say the word distribution, it probably is from the 2 infinity Selmer paper or the L infinity Selmer paper. And if I start talking about Selmer groups or Castle-Tate pairing or something, it's probably from the paper of Alex with Adam Morgan. Okay, and I should probably mention up front that like a lot of the stuff that goes on in these papers is much more general than what I'm going to talk about. I'm just going to try to keep us in a very specific case. Like you should think of a lot of the things that I'm talking about today, you could do them for the constructions with global fields. I'm just going to think about quadratic extensions. And yeah, so you should check these out for all the details. Okay, so as we heard in Julia's lecture, there's a conjectural distribution for the L part of class group of a quadratic field where L is some prime. But notably, we spent much of the lecture talking about the case where L is a good prime, which just means that L doesn't divide the order of the Galois group of your underlying extension. So for a quadratic field, that just means odd primes. And what I'm going to do today is I'm going to try to talk about the bad prime case when L is equal to 2. Now these were left out of Cohen and Lenstra's initial heuristics, and perhaps for good reason. We saw in the second lecture that Julia gave that there is some sort of like deterministic structure sitting inside inside the 2 part of the class group. So if I take K to be a quadratic field, then genus theory tells us that we know exactly what the 2 part of the narrow class group looks like. So the narrow class group, I'm just putting in some extra sign conditions, but you shouldn't worry too much about it. If I put an imaginary quadratic field, this is just the class group. If I put a real quadratic field, it's pretty close to the class group. I just have to think about a little bit with units and if the negative Pell equation is solvable. But basically, for a quadratic field, there is some sort of obstruction to randomness sitting inside the 2 part, or sorry, the 2 torsion. And shortly after Cohen and Lenstra put up their heuristics, Girth suggested an extension to them, which has a pretty, I think it's a pretty simple but elegant idea. So maybe let's specify the case of like, case imaginary quadratic, just to make our lives simple, and we'll just carry through with K being imaginary quadratic going forward, so I don't have to think about units or anything like that. And so Girth suggested maybe if I just kill the 2 torsion, then what's left behind behaves randomly. And when I say behaves randomly, I mean in the sense of the original heuristics, that groups are appearing inversely proportional to the size of their automorphism group and everything like that. And it turns out that this is actually correct. And the way that I'm going to frame studying this question is in terms of something called the 2 to the K ranks of this class group. And for the definition of that, I'm just going to say, okay, if you give me some K bigger than or equal to 1, then the 2 to the K rank, oh, I should probably not use K twice, 2 to the T rank of my field K is just going to be the dimension as an F2 vector space of the 2 to the T torsion where I almost kill everything. I push it right near the end, and then I get an F2 vector space, and I'll look at the dimension. Now, if you've never seen this definition before, it's related very intimately to the structure of the two-part of the class group in a very nice-looking way. The two-part of the class group, it looks like some z mod 2 z's, and how many? The 2 rank minus the 4 rank, plus some z mod 4 z's, how many? The 4 rank minus the 8 rank, and so on and so forth. So if you get bored at some point during the talk, you can just think about why that's true. And our ultimate goal is going to be to determine the distribution of these ranks, and so as a consequence, essentially determine the distribution of the group itself. Okay, does that sound all right to everyone? Okay, and I guess I should just mention that these are descending. As t goes up, they're getting possibly smaller, but they're definitely not increasing. And so the main theorem that we want to get to, is like kind of in quotations, because I'm not actually going to really prove anything. I'm just going to prove a bunch of results that tell me that I have a big machine I can apply to get this theorem. Is a theorem of Alex. And it says, okay, if I prescribe some ranks, 4 rank, 8 rank, 16 rank, all the way down the line, where this is, these are non-negative integers, then what's the probability that I have a imaginary quadratic field whose sequence of ranks looks exactly like this? And that is determining, again, the group structure of the two-part. And what I get out is an expression which will look familiar to you from Alex's earlier lecture. And I'll explain exactly what it means in just a second.
So k is just q and negative d.
Oh, yeah. Thank you. About that.
You also might need a 6 for pi squared or something.
Okay, yeah. Right. There might be a constant missing somewhere. I could have copied this down incorrectly.
Is there anything funny with like d 1 mod 4 versus 3 mod 4?
Pardon?
Is there anything funny with like d being a fundamental, like 1 mod 4 versus 3 mod 4?
No, I think it's fine.
Yeah, it's just the fact that you're using square free instead of all
Yeah.
positive integers.
How about this? How about we just we'll kill square free and we won't worry about the constant yet. Okay, and this p mat, it looks quite a lot like something that Alex defined in his first lecture. It's the probability that a randomly chosen n by n matrix with F2 coefficients has kernel of rank j. And then this p r4 infinity is I just take this probability and I take n to infinity. And so staring at this, I mean, it's an interesting looking result. It comports with exactly what Girth predicted, even though I didn't write down Girth's prediction. It exhibits some Markov chain behavior, and what's perhaps most interesting to us is that it looks exactly like the to infinity Selmer result that Alex put on the board a few days ago. And this isn't actually a coincidence. They're sort of like lurking in the ether for a long time. There's been like a feeling that the distribution of these 2 to the k Selmer groups and 2 to the k class groups of imaginary quadratic fields should work in like exactly the same way. Like these objects look very similar, and I think a very like down to earth explanation, or not explanation, but like exploration of this heuristic comes from some past results about 2 Selmer groups and 4 ranks. So in the 90s, Heath Brown proved some distribution results about 2 Selmer groups in quadratic twist families. And the way that he approached this was he just took his 2 Selmer groups, did 2 descent, got out some explicit equations, and worked out, okay, how many local points do these equations have on there? And he could study the size of the Selmer groups in the twist families. And the equations that got spit out were these conics, and so it ended up being, when you work through the calculation, that this distribution of the 2 Selmers is very intimately tied up in some distribution of Legendre symbols. Now, we heard from Julia yesterday that if you do this sort of number field or class field game to try to figure out what the 4 rank would be for a quadratic number field, that at the end of it, you're studying a problem about, again, the distribution of some Legendre symbols. And when you get through like a lot of the gridding details in Alex's papers, this is what you find in the middle. Like the analytic heart of it is, I have some Legendre symbols and I want to study their distribution in specific sums. And so there's like a constant visual cue to you that these are all the same. So when Alex first proved this theorem, it was in a paper where he also proved the 2 infinity theorem, and there the treatments of the 2 theorems they're similar, but it's not exactly the same. Like it's again proceeding a bit by analogy. But what's nice is that in the follow-up work, which is the L infinity work, there's a general treatment of everything in terms of Selmer groups of quadratic twists of Galois modules. And what I want to talk to you today about is, where do class groups fit into that picture? Because it's kind of clear where Selmer groups of elliptic curves fit into that picture. We're already talking about Selmer groups, so working in a slightly more general context, it's sort of clear where they come from. But where do class groups live in this? And I guess the very first thing I want to try to do is try to show you that the class group is a Selmer group. And I'm going to be using Selmer groups in the sense that Alex was talking about yesterday, where I'm going to take some Galois module, going to decorate it with local conditions, and study the associated Selmer group. Okay? Before I start going to that, does anyone have questions about the preamble setup? No? Cool. I also have a tendency to write small on the board, so if if the font starts to shrink, you should let me know. Okay, so we're going to stick in our imaginary quadratic extension world, and I'm going to try to show you a particular Selmer group. So I'm going to take as my Galois module the p-adic numbers mod the p-adic integers. And I'm going to give it a trivial GK module structure. As in all the other talks, this is just the absolute Galois group of K. And for the local conditions, I'm going to take them to be the most boring thing possible. Unramified everywhere. Notably, this means that this is an acceptable definition, right? We had to be unramified almost everywhere, and we're ramified everywhere. Okay, so what Selmer group does this spit out? Well, let's just remind ourselves of the definition. I take the kernel of this map from my big H1 into all my local H1s, mod my specified decorated local conditions. So what's nice here is that because M is a trivial GK module, these H1s are actually HOMs. And now it becomes a little bit clearer about what this Selmer group is actually going to be, because I'm just looking at homomorphisms from the absolute Galois group into Q mod Z. Now, on the one hand, I know this is going to have to factor through the abelianization of GK, because I'm landing in somewhere abelian, so that's totally fine. And then on the other hand, by the way I've picked my local conditions, this map is unramified everywhere. And so it's not just going to factor through the abelianization, it's actually going to factor through the class field, the Galois group of the class field of K. Or in other words, like the Galois group of the maximal unramified abelian extension of K. And so this really looks like homomorphisms from that Galois group sorry, these should be L's, not just Q mod Z. And what is this? This is literally the L part of the dual of the class group. And so I've succeeded in my initial mission. The class group is a Selmer group. It's not even a Selmer group in a particularly contrived way. This is like kind of one of the simplest structures that I could put here. I put a trivial module. I took basically no local conditions, and it spit out my class group. Okay, that's nice. But you'll notice something. You'll notice that I'm making sure to include some sort of base field here where I'm writing the Selmer group. I'm doing this because later on we're going to try to change the module structure and see what this does to the Selmer group. But what you should think about right now is that the kind of distribution results that we've been hearing about in the context of elliptic curves and the kinds that exist in Alex's paper are ones where I'm looking at Selmer groups in a quadratic twist family. Here, there's no clear twisting going on. The field over which I'm taking my Selmer groups is constantly changing, and the module structure inside doesn't really look to be twisting at all. So what I want to do in order to actually get to some kind of distribution result is I want to take this Selmer group and move it from having this extension being the thing that's changing around and have it to my module be the thing that's being twisted around. And that's where this field change idea is going to come from. So I have a GK module, and I know that GK lives inside GQ, and so I can induce on M a GQ module structure in the sort of natural way of if you've ever studied some representation theory. I'm just going to tensor it with the appropriate group ring. And now, with this induced module, I'm going to try to convince you that the Selmer group of K of M and the Selmer group of this induced module over Q are actually the same thing. So claim is that if I just take the Selmer group of K of M, then I can switch the base at a cost of possibly getting a more complicated looking module on the inside. And this base change, field change, is more or less what Alex's second paper with Adam is about, and exploring some consequences of that. Now I'll just note, like, these are actually supposed to come with local conditions, and if I base change, what happens to the local conditions? I would say don't worry about it. Basically, like, what's going on here is this isomorphism is coming out of the Shapiro isomorphism that was mentioned prior to this, which relates H1 of the smaller module with H1 of the bigger module, where I look at some fixed structure. And there are local versions of these Shapiro isomorphisms. And the local versions, I'm just going to pass the local conditions from this module over to this module by Shapiro. And so what should really matter to you, because right now we're thinking about unramified local conditions, is I'm passing unramified local conditions to unramified local conditions. Nothing's changing there. Okay. Okay, so that's nice, but maybe it's not quite enough yet. Like, it should maybe be clear that the way that K is going to influence this group structure is probably via its quadratic character. Otherwise, there's like no real reason that, like, there has to be something that distinguishes that this M came from a GK module. And so maybe somewhere inside of here we can see the twisting action. And to that point, then I'm going to claim that there's an isomorphism where this induced module, its module structure as a GQ module, is actually another copy of itself with the trivial action, and a copy of itself with the twisted action. The way to think about this is that here everything sort of breaks up into two pieces. One coming from like a trivial automorphism on K, the other one coming from the non-trivial automorphism on K. And you can kind of pass these two things over to this side, keeping track of the action with a minus sign. Right, this is just keeping track of the fact that my twist is going to send this sigma to a -1. And this is nice, because now if I take the Selmer group of this, I get some sort of fixed piece, a Selmer group that isn't changing, and then I get a Selmer group that's changing in a quadratic twist field. Okay. So if I apply this in the case that I've been working with the M is QL over ZL, then what I end up showing is that the L infinity part of the class group looks like the L infinity part of the class group of Q, which is nothing, and then some twist family. Okay, that's almost good enough. It's almost good enough, but it's not quite good enough because of the L is not equal to 2 restriction. I told you I wanted to think about the bad prime case, and I really do want to think about the bad prime case, because in this case of the good prime, we have this sort of issue that Alex mentioned in his first lecture when there was like a subsection titled Y2. When L is not equal to 2, we have some sort of base layer problem. We don't have a good handle on the first layer of the distribution that we need in order to be able to control the twist families. And so we're going to have to actually take L equal to 2. And we're not going to be able to apply the twist results about gamma modules to this, unfortunately. And so all hope is not completely lost though. We can kind of use this decomposition. The map that I described for you is still surjective, but because multiplication by 2 is not an injection on the module M, it's not injective anymore. There is some kernel there. And I lost my notes. Okay, here we are. Okay, so instead of a nice isomorphism, I get a short exact sequence. Okay, and the kernel being exactly this 1/2 just comes, if you think about looking at these pieces of the map, like when can this be, what gets sent to the kernel and what doesn't, you can just do this computation. It doesn't take too much time. Okay, I have a short exact sequence. It's kind of useful. If I hit it with the long exact sequence from group call homology, I can take that and then pass it down to a little bit of a sequence of Selmer groups that only give me 3 terms. I guess, all right, L's 2 here now, so I'm just going to 2. Okay, this is something. I have my class group almost being related to a quadratic twist. This part is 0, so don't worry about it. Almost being related to a quadratic twist. I have some kernel lying around, but like a 3-term exact sequence doesn't really tell you anything. And so what I would really like is to be able to add like 1 extra layer. And I'm not going to talk so much about the about exactly how we get this last layer, but what I'll say is you're going to hear tomorrow in Ariel's lecture on the Castle's tape pairing that associated to short exact sequence of Galois modules like this, we could come up with a pairing of the Selmer group of this term and the Selmer group of the dual of this term, which is, when you plug in all the usual elliptic curve stuff, is the Castle's tape pairing that you're familiar with. And this pairing gives us a way of relating this last term with the Selmer group attached to the dual of this last term. And star. So associated to star is a Castle's tape pairing. Okay. It gives me a relationship between this guy and the Selmer group of the dual of this guy, and most notably, is that the left kernel is exactly the image of this map in here. Right? Yes, that is right. And so I can.
Selmer groups.
Oh yeah, sorry. Yeah, you're right. The Selmer part, yeah. So the left kernel is the image of this guy in here. And so I can now just apply the castle state pairing and extend this sequence one more step. And what I'm left with looks like this. Okay. And okay, now we're actually in business, because if I can understand this last term and I can understand perhaps the kernel of this map, then I'm going to get an actual decomposition for my class group. So what's nice is that at least on the level of a module, the dual of this is mu2 or C2 plus or minus 1. And attached to that is a certain set of local conditions, which I have to look at the orthogonal complement of. And if I chunk my way through the computation of what exactly those local conditions are, and then I use the fact that my module is just the 2th roots of unity, then I can work my way through this calculation and I can find out that this term actually vanishes by Hilbert's theorem 90. This last term is a 0. Now that's actually really good for us, because now if I want to get an understanding of a decomposition of my class group in terms of this quadratic twist, actually all I need to do is finish the computation to see what the kernel of this, this last map is. Okay? And if you do it, then what do you get out at the end? Where the kernel of this map is actually just the invariant points under the Galois action. And this gives us a distribution, or sorry, a decomposition of the class group into something that maybe you should expect heuristically. This is essentially what Gauss's genus theory computes, the invariance of the two-part of the class group. And so what we've put up here is say like the two-part of the class group decomposes into something in a twist family, which you can use the big distribution theorems about Selmer groups of Galois modules and twist families to say this is like the random part, which obeys this Markov chain behavior. And then I have some sort of fixed genus part sitting in here. And this is exactly what you would expect at a bad prime, which is nice. And so if you apply this theorem and you combine it with Alex's results about distributions, you recover that result that I put up on the board a while ago, proving Girth's heuristic in the L is equal to 2 case. And I'll just say, if you're worried about the fact that there's a bunch of duals here, this dual and the class group are related by the reciprocity pairing. So the class group is isomorphic to the Galois group of the Hilbert class field over K. And so we can pair things back and we can relate this right to the class group of K. And I think that's everything that I have to say. Are there any questions about anything?
Which dual is the check?
Oh, okay. The check is the dual that Alex defined yesterday. We're taking, yeah. And then sort of sitting inside of that dual is like this thing with local conditions where when I define the Selmer group of the dual, I don't just have to define the module, I need to define the local conditions as well. They come out of what Niven talked about. The local conditions associated to the dual are the orthogonal complements to your original local conditions.
Any other questions?
And you twist and dual before taking Selmer.
Yes. Yeah.
So we should thank the speaker and thank the speaker again.